Welcome back, everyone. Now, this time for the second part on the topic of correlation clustering. As a brief recap, what have we approached in the last session? Well, we were first discussing on the topic of what is the difference between axis parallel subspaces and arbitrarily oriented subspaces, knowing as the difference that axis parallel subspaces are tailored at detecting clusters that reside in subspaces where feature independence between the dimensions is assumed, while on the contrary, in correlation clustering or arbitrarily oriented subspace clustering, the clusters reside in arbitrarily oriented subspaces where one assumes that we have a linear dependence, or in other terms, a correlation between the features. Then we moved on to the topic of local PCA as a motivating example. Well, beforehand we also discussed about the correlation subspace and the orthogonal cluster subspace where the objects are most dense, and correlation subspace as the axis with the highest variance where the objects actually exhibit a correlation between it, and moved on to one of the first correlation clustering algorithm known as local PCA. From there on, we moved and have seen in this one diagram the taxonomy where you have like single subspace optimized and multiple subspace optimized correlation clustering, and that it is also kind of used in different areas. So local PCA in its origin has been used for the purpose of detecting nonlinearities or nonlinear structures within the data through piecewise linear approximation. On the contrary, in manifold learning, for instance, locally linear embedding is used to capture manifolds in the data, which is also some kind of nonlinearity or as a nonlinearity in the data set. And we've seen that there are plenty of algorithms. And the question that we had there, do we really need to go through all of these algorithms to know them by heart, know about all of these, each single for loop and if else statement and so on? The answer is, of course, no, we do not need. Instead, we focus on a handful of algorithms, namely OCLUS, which is like local PCA partitioning. So it's a K-partition algorithm, then a correlation clustering algorithm. Then we had 4C, an algorithm which relies on the density-based criteria from DBScan. And then a cache as one special case, which is not relying on the PCA technique, which is inherent to OCLUS and 4C, but relies on a so-called Huff transform. And but then we got a bit more into details about the Huff transform and the properties, and that, for instance, if you recall, if you have two segments or two dense areas which seem to be on the same line, they will be discovered as one correlation cluster by cache, because it is not capable, unlike 4C, to capture local densities, but is a global correlation clustering algorithm. In terms of local, global, dimension hierarchical or density hierarchical, these are things that we will cover in this week's videos. So now we proceed with the topic of Huff transform, since you know that I share a kind of an obsession with that topic. And you may have heard about like that the representation, if you recap the representation of each object in data space, each data point corresponds in half space to a sinusoidal function, to a trigonometric function. Now, why do we have this sinusoidal function? Wouldn't a simple representation as a line suffice? Or what are the reasons for choosing that specific representation of the half space? Is it the only one? The answer is obviously no, but how do they differ? And this is something that we'll approach here in the next step. So we've got here like a matter of representations, the slope-intercept form. The slope-intercept is probably the most simple, yet at the same time, that one which comes with most of the issues. So there are several ways to represent linear functions, and we have something what we are dealing here with is a slope-intercept form, the polar form, polar representation of the Hessian normal form H and F, and the Hessian normal form. So what are the advantages or disadvantages, and what do they actually mean? As an example, a line can be captured through the slope So how steep is it going up or going down? As you can see here in this part. And we have the intercept, t. So we have m as the slope and t as the intercept. So where does it intersect with, in this case, like the vertical axis? And so if we have here one point A, it is represented as this line here. And it means, you see here on the axis, the half space is spanned by the axis m, representing the slope, and the axis t, representing the intercept that we have here. So what we see here in half space is basically all possible lines at all different slope-intercept pairs. So like here, one slope is like -1 and intercept is 4. Then here another one is like, let's say, here it's 2 and as the so intercept, and as the slope we have here 0. As the slope we have 0, yes, sorry. And then we continue like that. But the question is, does this red line truly capture all possible slopes and all possible intercepts? And the answer to that is it doesn't. But why? The reason is, if you would want to capture all possible slopes and all possible intercepts, these two axes, m and t, would go up to infinity. So they would go here from 0 to plus infinity and to minus infinity, and from 0 to, for the slope, to plus infinity and minus infinity. So in other terms, the half space itself is unbounded. And if you want to look for these intersecting areas, they may be everywhere. They may be here locally nice, or they may be somewhere at 1 billion and 2.5 billion slope and intercept. So we have here an issue that we do not know how big, how far should we look at. It may happen that we say, look, we start from -1 billion to +1 billion, but it may not be enough, because 1 billion and 1 is actually the region of interest we are looking for, the region of intersections. So the slope-intercept form is simple and intuitive. This is how you think of a line. It has a slope and it has an intercept intersecting with the vertical axis. It enables a fast computation for the regions of interest, and it fulfills this point-to-line mapping property. What does this point-to-line mean? It means that one point corresponds to one line, which it does, and one point here. So let's say this intersection point I corresponds to one line here. So you have exactly one point in data space corresponds to one line in in half space, and one point in half space corresponds to one line in data space, in this original space. However, it can't deal with y-axis parallel lines. This is also one issue, because if you would have one line that is like here, perfectly vertical, what is, here, if you would have one line in data space which is perfectly vertical, what is the slope of that line? It's infinite. So it has an infinitely high slope, and this would mean that this axis here would go to infinity and the computer wouldn't quite catch it. It's not suitable for higher dimensionality, because we stumble upon ambiguities if we just increase the number of slopes. If you keep adding slope m0, m1, m2, m3, m4, and it is unbounded in its parameter space. As we said, we can choose for the intercept t and for the slope m arbitrary high values, and still not be sure if we captured everything that we need. Therefore, that may emerge the polar Hessian normal form come on the stage, and here we have like a different representation. The idea behind this polar form, which is also utilized in cache and also in many other computer graphics applications where half transform is involved, we characterize here a line with ABC through a trigonometric function, through a sinusoidal function. And this function, the semantic behind is, it captures, like, on the one hand, the distance from the origin orthogonal to that specific line in data space. It has to be here orthogonal, so an angle of 90 degrees. And on the other hand, we have like this angle that is enclosed between one axis, or the closest axis that the x-axis that we have here to that particular orthogonal line, to that distance, to the actual linear correlation that we have. And so we have here one angle alpha, and we have here the distance delta, d or delta. And the computation is d equals y times sine of alpha plus x times cosine of alpha. And it can be, of course, also generalized to arbitrary dimensions, as it has been done in cache. So one major contribution in cache is that it has been generalized not only to 2D, because on images 2D is actually of interest, or at maximum 3D, but generalized to arbitrary dimensionality. And you can also go the other way around. So given an alpha I and a delta or di, you can like map it to x times cosine of alpha I plus y times sine of alpha I to get actually this one particular line captured here. And you see now how we've got here these sine and cosine functions as trigonometric functions and how they intersect here. You may rightfully say they look kind of more complicated, because a line is something simple, it's something easy to calculate, and now these nonlinear, these trigonometric functions seem more difficult. Yes, it is indeed one of the weaknesses of this representation. Nevertheless, what we have here is that the angle is bounded, because what do we know about angles? Angle is something between like 1 and 360 degree, or 0 and 360 degree. This means that any of these angle axes, like alpha 1, alpha 2 in high dimensions, alpha 2, alpha 3, and so on, all of them are bounded. They cannot go beyond pi, so to speak, or beyond a certain threshold. And in what is still unbounded is the distance delta. So this is still something that we may potentially miss. However, here you can also like derive and ask, what is the maximum deviation of that object to the farthest point? So you can ask, what is the farthest point available in the data set, and take that as a maximum. So here also you can kind of provoke a bounding. However, angles here for the alpha are naturally bounded by the properties of angles themselves. So the polar Hessian normal form, it is bounded among all axes in parameter space except D, and here you can use as a heuristic the furthest lying point. It can deal with y-axis parallel lines, because if it's y-axis parallel, then you have like here 0 degree, you have here 90 degrees, sorry. So if 180 degrees, sorry. So if you take this D, this line that we have here, and you keep rotating, 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 so that this line becomes perfectly vertical and parallel to the y-axis, then you have like 180 degrees. And this is here easily to be captured or to be represented in the angles. It's suitable for arbitrary dimensionality, as it has been shown in the cache paper. However, it has not this point-to-line mapping property. So you still need to convert it. What does it mean actually? It means a point here corresponds to a sinusoidal curve here, but a point here corresponds actually to a line. So you have point to curve and point to line. So this is not an exact mapping as we have in the slope-intercept. In slope-intercept, in the previous case, it was like a point corresponds to a line here, and a point here corresponds to a line there in the original data space. This point-to-line mapping property is broken. In our cases, like for clustering or for data mining, it doesn't make that much of a trouble, because you can easily translate this function here, this sinusoidal function, this polar representation of the Hessian normal form we will turn to. This you can easily translate into the non-polar or the Cartesian Hessian normal form. However, the computation of regions of interest is expensive. You need to compute several derivatives, especially in high dimensions, to see if it intersects actually a hypercuboid or cuboid or a rectangle in half space. And it's kind of non-intuitive, because, to be honest, it's difficult to wriggle your mind around of saying, okay, now these 2 points, they are these 2 sinusoidal functions that intersect. It kind of gets difficult. Not well. And there is the last type of representation that we introduced here is the Hessian normal form, so the non-polar, the Cartesian variant of it. And what we have here is like the normal vector n, which is like here, this one that we have, the normal vector or the direction of that we are capturing. And again, the distance, which is like from the origin orthogonal to that particular linear correlation. However, what we can observe here, we get like one additional dimension, because if we have like A and B, then we have also like this distance D. So it's like 1, 2, and 3 dimensions that we are capturing. So we have one in the one direction, the translation, so to speak, then the other direction. These are the two axes here, A and B, that we have. And for the distance, that's what we know from the other representation, from the polar representation, we have this D axis. And if they intersect, then we do not have an intersection point, but an intersection line, because hence they are one-dimensional larger. And the computation is kind of quite simple, because you say the distance delta here is like the linear combination of the x coordinate of a specific point, like let's say the point C, times A, times this direction, plus the y coordinate of this point C, like 3 times B, this direction that we have here, or this distance, to be precise. And well, the Hessian normal form, it's bounded among all x's in parameter space except D. Why is it the case? Why can we say that it is bounded? Well, you can normalize a vector. So this direction vector with A and B, you can say you want to divide it in such a way that the length of the thingy here is like a unit length, is n. So you can enforce a bounding. It can deal with y parallel lines or axis parallel lines, is suitable for arbitrary dimensionality. It fulfills the point to line mapping property. Well, not exactly, because a point here corresponds to like a plane here and not a line, and a line here corresponds to a line here. So it's also kind of an odd mapping. However, the things that we have here, like a line to a line or a point to a plane, they are all of linear nature. So we kind of have a satisfaction of this point to line mapping property. And the computation of regions of interest is inexpensive, because you're also here, like in the slope-intercept form, dealing with normal, with linear vectors. However, it requires linear representations. It requires one dimension more in parameter space. Well, I mean, it doesn't make that much of a trouble, because if you have 100 dimensions, then you will have in half space 101 dimensions. So one dimensionality more is not actually having that an impact. Yeah, and this is actually it for the 3 types. But what is the take-home message? Now you can say we have here the slope-intercept, the polar, and the Hessian normal form. Well, the answer, or the take-home message here is there are different representations possible. There does not exist the one representation. There is even, I think, a paper by Spectrum publisher that states the fan projection or fan out beam fan projection, and there's even one Möbius strip projection or representation of the half space, and so on and so forth. So there are totally different ways of representing space for which we aim to capture linear patterns in our data set. Which one to choose? Well, it depends. I personally, out of getting used to it, I use the polar form, to be honest, at that stage. However, if you get in cases where you say, no, it is simply too expensive to compute if the sinusoidal functions intersect actually a cuboid or a rectangle or hypercuboid, then you probably do not wish to go for the polar form, but for the Hessian normal form. And if you're like dealing with images, then you can also say, you know what, I'm kind of happy with the polar form, because it still can detect like lines with infinite slope, so y-axis parallel lines, and since it's only 2 dimensions, it's not that expensive to check if there's an intersection with a cube or not, or with a cell. But well, this is so far about this topic. It's not that of a major topic, but more of, hey, look, there exist several representations of it. But I hope it gives you a bit of an insight that what you see in the cache paper is not the only way of representing a linear half space. Well, stay tuned for the next session, and thank you for your attention.